Right. Did you have a look at the exercise? Any clue which could be the answer to this exercise? Someone want to come here and enlighten us about the solution of the exercise?
No.
If someone doesn't want to come, I have to pick up someone randomly between the audience. Come on, it's easy. You're a strong and clever guy. You will do that in 3 minutes.
I always get 15 minutes.
Now, at the figure I've been given you is a I will say, simple sinusoidal function that is, they look like quite constant, and in terms of the properties. And the first question was describe for each of the sinusoidal function in figure 1 the frequency. So period defined at peak to peak, and note the time scale is in milliseconds. Please.
Right, okay, so yeah, I used the equation with the frequency is 1 over the period. So then I just looked for the time taken out to do one complete cycle of the wave. Plugged it into the equation and got 25 hertz for the top one.
Yep.
16 hertz for the middle, and 10 hertz for this one here.
Any complaint? Everybody
Did you
happy?
break it down? I know there's a few of us who didn't really get it at all. So kind of skipped over exactly what you did.
Yeah, sure. So 10 or something.
Don't write in there.
So yeah, the equation is the frequency is equal to 1 over the period. So it's the 1 is for like it's like 1 second, this amount of cycles per second, and to get your t, the period is, so you look at how long it takes to do one complete cycle, so peak to peak or trough to trough, for example. So I think I use these, so that's about 10 milliseconds. So go 10, 20, 30, 40 milliseconds.
It's not, it's 16.6.
Yeah, because there's about 13 lines.
There's 12 lines.
The scale.
Always 50 milliseconds. Oh, they are right. Yes.
Are they?
Well, but fair enough. The methodology is correct. Now, yes, yeah, because it's 50 milliseconds. So it's 25 milliseconds the half of it.
How is that? Because I thought it was 50. It's like that's the gap is 50 milliseconds.
Yes.
From there to there.
Yeah.
Ah, right.
Right.
Yeah.
So that's the. So if you divide into 2 is 25, and then the rest is just the subdivision. Then.
Yeah.
So how much you got? 62, 40, and 20 hertz. Right. However, so clear how you calculate graphically a frequency having peak to peak, trough to trough. The second question is which of the frequency obtained in A is within the range of exploration seismic experiment? 60. Why not 40? All of them. Exactly. So all of them are within the range of the seismic exploration. Remember in the previous slide, I told you that most of the seismics now run between a kind of 0 and 100 hertz. So everything between 0 and 100 hertz, with most of the noise that are the ground roll noise localized in the lower frequency, but most of them can be physically within the range of the seismic experiment. Okay? Now calculate for each the sinusoidal function of the wavelength peak to be assuming the velocity v of the signal wind in the medium is 2,500 meters per second.
I've got it wrong because I've used the
Yeah,
wrong scale.
fair enough. But how did you manage to do it, basically?
So I used the equation of the velocity is equal to the frequency times the wavelength.
Yeah.
And then just rearranged it for wavelength.
Okay? Any complaint? Any problem? So how much the value of the wavelength you got?
41.85,
Fine, yes.
and then 63.5 and 125 meters per second.
Good. So it's a meter. So as you understand, the wavelength of this frequency are ranging from the longest wavelength, that is the one with the lower frequency. That is of the order, those are a frequency of the seismic scale. So, the frequency of the seismic scale. So, it gives you an idea which is the resolution that you can expect within the seismics, basically, exploration. So, using the frequency in between 0 and 100 Hertz, which are the resolution, so the wavelength scale, so what a front of the wave can perceive in terms of dimension, are objects between mostly 20, 40, 60 meters. Now we will see further on to the next lecture that in reality the natural system is much more friendly to us. So a wavelength can basically recognize an object that is within the dimension of the wavelength divided by 4. So the lambda 4 is the tuning thickness. We will learn that in the next lecture. I anticipate you, as now you got the concept of the wavelength. So if you take the value you got, you divide it by 4, you got the minimum, basically, resolution, so the best resolution you can get at the various frequency for an object that has a velocity of 2,500 meters per second. So my question is, what do you need to have in order to have a really good resolution? Where will you go in the seismic data set? Suppose you got a seismic in times offset, where will you go to look at to have the best resolution? Pardon?
High frequency.
High frequency. So where will you go in the high frequency? Down or in the shallow part? Shallow part. So that explains to you why in the whole stack seismic line, as soon as whatever has been the processing that has been playing with, the best resolution that you got are usually in the first upper part of the seismics. Because they retain the highest frequency, and whatever is the velocity, well, there is one object, one parameter that is playing against that story of the high frequency on the top part. Remember that the resolution is related, the wavelength is related somehow to the velocity. So suppose you are in the shallow part with high frequency, but you got a lot of gas inside. The gas is slowing down the velocity. So one of the reasons why you see, for example, the seabed on the seismic scale with a very poor resolution, despite its very high frequency, is because the velocity of the seabed is lowered down by, for example, pop marks or intrusive component of the gas. If you got gas, the gas is slowing down basically the velocity. You can get velocity lower than 1,500 meters per second, sometimes 800 meters per second. So you understand that if you got a frequency of 80 Hertz and a velocity of 800 meters per second, well, your wavelength start to lose resolution even in the basically shallow part of it. So it's the combination of the two. Okay? Right, so the last question is, do the sinusoidal function in figure 1 shows the same phase? Yes, no, motivate your answer.
The top two, I think, are definitely not in phase.
Interesting. That's fine. Now, my question is, how do we define two objects in phase? My suggestion is you choose a reference system, whatever you want. Assume, so let's choose, so we have to define me. That answer is a little bit, you have to be a little bit ruse, that answer. Because the answer would be, the answer function in figure 1 shows the same phase. The answer would have been yes or no, depending which reference system I'm using. So if I'm fixing my reference system, for example, in 0, so I'm fixing, I'm observing the tree function in 0. Are the tree function in 0 in phase? Are they all at the peak phase or the trough phase?
Yeah, they're.
Boom. So if I'm at 0 instant, I'm sampling my function at 0 instant. At 0 instant, I'm arriving at the tree signal perfectly in phase. Where do the signal change? Basically, its phase is as soon as as you observe, they got a different frequency, they got different cycle. So as soon as I'm sampling, for example, at 25 millisecond, well, at 25 millisecond, the signal I got it are not in phase anymore, because the third one is a trough, the second one is a peak, the first one in a trough. So only two are in phase, the other one not. So this is important because the concept of phase require at least to compare at least two signals and require to define a reference system with respect to what I'm observing or sampling. Okay? Because I'm assuming that a signal is always in phase with himself. And that's no discussion about that. Okay? Is that clear? Very good. Thank you very much. Right, so more or less that has been digested. Easy. Go. So now you know a little bit how to use this kind of concept quickly in a dirty way. As you see, that concept quite useful if you start to interpret the seismics. But we are going to go there slowly. Now we are going to enter in the probably the harshest part of the course, because it's the part where you got a lot of kind of small calculation, mostly related to trigonometry. They are not complicated. I will stop at a certain point to remind you the basics of the trigonometry, that is the sinus, the cosinus, the tangent, what they look like, what they are, or you calculate them very quickly. They're very bright, so you will understand it in a microsecond. So in a couple of seconds we can move on to the object. In any case, we stopped after 1 hour. You have time to breathe and think about and digest it. Don't be confused by the calculation of it. It's a lot of trigonometry. So at the end of the story, what I want you to understand is how you get there and why some solution that they are going to use to do exercise, they got that solution. So think about it. I'm never going to ask you the demonstration of it, but what I'm asking you is to play with the parameter. Once you go with those one, you're done. Okay? So, lecture number 2. What I'm going to introduce you is the concept of, well, let's say we have seen what are the P and the S wave. We have seen also the surface wave. For instance, we are not playing with the surface wave except, if you want, for a little while I introduce you the refraction, in which the refraction for a moment, for a while, they are behaving as a kind of surface wave. But they are not, strictly speaking, surface wave. They are head wave that come from a body wave, but they are basically misbehaving by basically moving across a discontinuity. That's the only instant in which you have to deal with this kind of beast, but that's fine. Okay? And you will see that beast, in fact doesn't behave strictly like the PNS wave from a kinematical point of view, but step by step. Partitioning of the wave into a discontinuity, we will see that in 2 steps. The first step I will give you introduce the general law without the math. We will use a simplification of it when the wave is perpendicularly or orthogonally reflecting to an interface, that is simplify a lot of equation. We will reapprise this concept with another simplification when I introduce you the amplitude versus offset, or the AVO. Is a technique widely used in the industry or misused in the industry as well, but is using the whole other part of the moon that we are not looking at mathematically in details. Okay? Reflection and refraction is a consequence of the partitioning. Acquisition, just a star velocity in rock, we will see. Remind you the difference between the P and the S wave. That's important. The P and S waves are 2 body waves. They behave in a different way. The body wave is basically got the vibration of the particle parallel to the direction longitudinal basically propagation. The shear wave not. The shear wave has basically the vibration component that is in any direction orthogonal to the propagation of the P wave. We have seen the S wave, we don't care, we have seen the... Now, what's happened when a P or S wave do reflect into a surface? Well, it's happened what you see in there. That's the reality. The reality is that you got a P wave that is incident at a generic angle respect to the surface like that. What I indicated there is the direction of vibration. As it is a P wave, the direction of vibration is parallel to the propagation, is reflecting, and as soon as it's reflecting, at a generic angle that is different from the zero with respect to the orthonormal, so every situation except the one orthogonal is there. We will see the orthogonal one is a special simple case we will play with. All this kind of situation, they are producing, in theory, so every time I got a P wave at a generic angle, is producing this kind of mass on the other side. The mass can be described in that way. It produces reflected waves that are a P wave reflected, plus, on the reflected side, a shear wave, which energy summated to the P wave constitute the full part of the reflection of a P wave. So every time you got a P wave that is reflecting at a generic angle, okay, in between 1 and 89 degrees, where 1 till the critical angle in which you start to not reflect, we will see that, it's a critical angle where you start to refract. Within the reflection, basically generic angle, it produces two rays that are two reflected rays composed by a shear wave and a P wave. The production of a shear wave from a P wave is called change of mode. So you got a change of mode of the P wave into an S wave. So basically, if you put a receiver on the top part of the of the system, and you got a multi-component receiver, the 3 hydrophone and the 2 shear wave components, so the 3 components of the receiver, the 3 components will basically register 1 pressure component plus surely 1 shear wave component. Not finished. Part of the game tell me that part of the energy doesn't go completely all into reflection. It goes through transmission as well. And the transmission behave in the same way. You got a transmitted part of the P wave and a shear wave transmitted to down. So every time you got a P wave that is reflecting in a generic way to an interface, is producing 4 objects. P reflected, change of mode, S reflected, P transmitted, change of mode, S transmitted.
Sorry, is the change of mode just the S wave, or the other P wave, is that a change of mode?
The change of mode implies that the P wave is transforming mode of propagating. So in that case,
Yes.
is the P wave changing into an S wave.
So just the change, so the other P wave is just
The other P wave is still a P wave and behave as a P wave.
Okay, yeah.
But it's part of the game. What you know, what you need to know, what you need to fix in your mind is 2 things that we are going to use later on for the simplified case. Is that when you got a first arrival of the P wave, all the initial energy of the P wave, so the total energy of that one, need to be balanced by the total amount of energy of the 2 objects there, 2 objects there. So it tells you a couple of things. 1, if the energy have to be preserved, that means that any sort of reflected transmitter are going to have less energy than the initial P wave. Okay? And it's telling you that every time you are reflecting against the surface, every time you are losing the P wave, or the S wave produced by that, transmitted or reflected, are losing a piece of the initial energy of the first incident P wave. As you can pretty much understand, for one reflection, that's valid, that behavior, for any sort of multiple reflection. But it starts to be complicated for a multiple reflection, because then any of those can behave like that one. So that one will resplit in another 4, and the shear wave will resplit in another 4. So for every reflection, you have a kind of multiplication kind of the shear wave. Okay? So basically, the second reflection will have that one, 4 component, transmitted and 2 transmitted, 2 reflected. P wave, same story, 2 transmitted, 2 reflected. So the 2 will produce 8, in total 8 animal. Then the 8 animal will resplit again. Now, in theory, mathematically, you can continue for a multiple infinite reflection. So you have a huge amount of million, basically, a certain point of ray moving, some in the shear wave, P wave, or whatever. What is the problem? The problem is that you are losing energy every time. So there is a limit beyond which, at a certain point, you are missing them. You are missing them because, as you are a geologist, you expect that in order to measure those kind of reflected wave, you need a certain point, you need to expect them coming back to the surface to be able to register them through the geophone. So, all the rays that are penetrating to a multiple reflection at a certain point, in order to be registered, they need to be reflected somehow. But the reflected component of those, in theory, they should be with a much less energy and they're losing energy proportionally to the number of reflections they got. And remember that every time they come back, they have to come back again through another transmission of the way back. So, in theory, you got millions of P and S waves. In practice, you are not going to be able to measure all of them because they have too low energy. A lot of them they will arrive as a kind of very low, if you want, frequency energy related components. Some of them you will not be able to recognize because they are too low energy. But that's the picture, the real frameworks in which you have to think of that system.
Can I just ask a question? Does that mean energy is then not conserved because you're saying that velocity changes as they keep splitting?
Absolutely, it's conserving. The conservation is done to the fact that every time you shoot the energy, you have to take into account that the energy is the summation of all the product. So, that one is going transmitted. You got another reflection, it produces another 4 components. The summation of these components agree with that one. But now the energy of that one is going to be different than the energy of that one because that one was a part of the total energy.
Of the total.
So every time you lose a piece.
Yeah.
So it's a kind of, so at that point you arrive to a kind of diffusion of the system. You lose basically. So in theory you should preserve, mathematically they still exist. Physically, well, yeah.
Just for the mode change there, say it's only go one way, so only P waves can go to S waves, does it?
S wave can change of mode and become a P wave. In fact, I introduce you to the possibilities that you got in your life, and all the possibilities are those. You don't need to learn them, you just need to see that they exist. Look, the first example. The first example is that you got a shear wave. The shear wave is going to split in a component that can be a change of mode without change of mode, like the one on top, or with a change of mode. So you got an incident shear wave that got an SP, that means shear wave transformed into a P wave. SS is a shear wave that remains a shear wave. SP shear wave that transforms into a P wave, SS in shear wave that remains S wave. So you can have the completely, I would say, specular opposite example in which the shear wave now is reflecting into a surface and is producing the full body. And again, you get the same problem of energy preservation. So those 4 components that are basically produced by the first one need to be equal to the total amount of the first one. So every time they are losing pieces. But as you see, it's quite complicated. The physics behind that, what I want you to appreciate, and that's the reason I want to introduce you, but we have the big picture, is that the physics of reflection for a generic angle is pretty much complicated. Because you have a kind of fauna or zoo of possibility in terms of reflection is pretty high. So, you can pretty much understand why the seismic industry had stopped quite before going into this kind of theoretical. There are publication and books that already describe completely and perfectly the theory of that. So there are books that describe all the mathematics of that. What's the problem, and that's a classical problem of a lot of geophysics, is that in theory you control perfectly the problem. In practice, to get and to test some of those residues is very complicated. You can test it in a laboratory, but as soon as you are moving your company as the PGS, CGG, for example, doing an acquisition, to To do something like that, you will see, I will introduce you when you introduce the acquisition, it costs millions. You need to think carefully the way you want to acquire. First, you need to have not anymore geophone with the simple hydrophone, but you need to have geophone with the 3 component or the 4 component. Second, you need to be sure that you have to track all this kind of basically array in a quite precise way. So you need to play with the ocean button cable stuff, completely fixed on the ground and measure it constantly to arrive at the PNS wave. So it costs. So the people, if you want to convince someone to catch all the components, all the change of mode, because you want to extract some of the properties, measure it by the shear wave, for example. The only reason you want to do that, honestly, is because you want to measure the shear wave. Okay? That's the only reason. Well, you have to have a very good reason to measure the shear wave. We will see, or we have seen already, that the shear wave basically it's a system that is very good and pretty much elegant in testing anisotropy. Transverse anisotropy necessarily requires the shear wave, because the shear wave has the property as the electromagnetic wave to split. And the splitting between the 2 components related is proportional to the anisotropy. But remember that as soon as you want to tackle the shear wave, you got all this kind of problem happening. So you are missing piece of the story. And you are losing energy. So you need to have a very, very sensitive geophone. Good.
David,
Yeah.
the change of mode of the incident ray, is it dependent on the type of interface you're in, or?
Mostly, the theories say that every sort of interface that has a contrast of impedance, we'll see that soon, produce a kind of change of mode. Where the property of the interface play its game is which kind of change of mode you are going to have. If you're having a change of mode like that, or you are having a change of mode of like that. It does depend in reality. Well, as you see, okay, let me be more precise. It will complicate a little bit the picture, but you ask me the question, I reply. P wave is a P wave. It's a compressional wave. It does reflect on the surface only one way. The shear wave, not. With the shear wave, you know, it's a polarized wave. So it can, it can reflect on the interface. But it can reflect on the interface being elliptically polarized along specific direction, you stack to another one. So every this kind of different wave of reflecting of the shear wave, because they are polarized in different orientation, are going to make the difference between this kind of scenario. So P wave is basically that one, but the shear wave, you see, you got several options in which she can behave, depending on how she's vibrating when she's incident. Where do the reflection property play the game? And is the ability of transforming the part of reflection into the component of the transmission. So depending how much is the contrast of impedance, you can have more or less transmission or reflection. Now, you got the big picture, you know that, good, that was the message. We carry on in a very simplified example. The simplified example is, let me enter with an example to give you an idea what is the reality, why we simplify the problem, and why. Because honestly, you are all geologists, so I need to introduce you, or the people need to introduce you, the concept of contrast of impedance in an easy peasy way, because you don't care about what the shear wave is doing in terms of phenomenology, and you are right. Because at the end of the story, you want to be sure you are measuring the most important things, the one that got the most important information. Good. Let's do some kind of estimation of that. You have a geophone, and you get, a source, okay? And you got a series of geophones. And you are acquiring, in a seismic exploration experiment, at the scale of a basin. So your name is PGS or your name is CGG, you're pushing a boat or in the desert, In Saudi Arabia, you are playing with the Sapka environment, so everything is pretty much flat parallel, no problem, no discussion. You are all sedimentology, you like that, you want to see what's below. Good. The distance between those objects are 25 meters, usually. At best, 12.5 meters. The thickness of the reflection of most of the reservoir are of the order between 100 meters or kilometers. So if I ask you to have an estimation of which is the angle that you expect to have in order to have reflection in an object that has 1 kilometer like that and has 25 meters like that. So I'm not on the scale, okay? This is 25 meters, this is 1 kilometer. If this is 1 kilometer and this is 25 meters, do you have an idea we can calculate the angle? Pattern? The tangent. So can you calculate me the tangent of that value? If you have a calculator. So you do a kind of 1 kilometer divided 25 meters. So and then you do the inverse. And you give me an idea of which is the angle of incidence of that object. So that angle, with respect to the normal, is 25 meters over 1,000 meters. You do then the inverse of the tangent, and you give me an idea of the angle, more or less. If it is 25 degrees, if it is 1 degree, if this is 5 degrees, if this is 60 degrees. So someone is outputting to me a 1.4 angle.
40.
Or 14. Fine. Can be 14. Everything for me that is below the 20 degree, honestly, is a measure. Are you sure it's 14?
40.
How do you know
The opposite is 25 meters.
25 meters is the geophonometer.
Yeah.
1 kilometer.
That's meters.
Yeah, the first. Oh, okay. I'll put it one there. So, numbers 1.4. Now, honestly, this is a realistic example of what's happening if you do an experiment. So, your angle, at best, to have a reflection, in that case, is going to be necessarily around 1.4 degree. If we are moving to 5 degree, even if we are moving to 10 degree, I think we are still around an almost orthogonal approximation. And 1.4 specifically is going to be something like that. So maybe if I try to simplify all the realistic system that is mathematically correct like that into a system that is like that, in which I think that a good approximation is an incident ray that is always almost orthogonal to the surface, that is going to simplify my life. Because what the physics say, that if you are around the orthogonality of the incidence of the angle, the whole change of mode disappear. And the only thing you got a reflected wave and a transmitted wave. Full stop. P wave. So, for our purpose, we analyze only the behavior of the P wave through the reflection avoiding the whole change of mode. If most of our experiment in this exam is going to run around this kind of angulation, why the hell do we want to complicate, and more important, me to complicate your life, to see all the kind of... if in any case they're not going to add anything. Because if you're around 10 degrees, that is far beyond even the example we are looking in there, That's fine. I can approximate it. So keep in mind that change of mode exists, but we assume our geoval measure only the P pressure wave, and in fact, as you will discover soon, most of the pre-stacked and stacked seismic dataset are using strictly the P wave. They don't use the shear wave. So they are assuming that most of the energy is basically registered by the P wave. Good approximation. Look, it's a pretty good approximation. Now the complicated stuff. Here, now we have to go to the equation. Now, remind you what is the starting point of the equation. The starting point of the equation can be or that one or that one. They are perfectly equivalent. Remember, the A is the amplitude, the sinus is the sinusoidal function, the K is the wave number, V is the velocity. We know that the velocity multiplied the wave number, that is the inverse of the wavelength, is nothing else than the frequency. So I can rewrite it as a frequency. You can think as a cyclical frequency or as a normal frequency. Details for mathematicians, we don't care. K is the wave number, is the wave number that comes from the multiplication of that one. That's is the component that in the previous exercise I've given to you at all is the one that is deciding if a wavelength is dephased or not with respect to another one. If they got that bit different, they are dephased one respect to the other. In fact, this is a K wave number, this is an X space, so this is the space dephasing that you are measuring in a diagram, amplitude, space. Okay? This is the frequency, is what is defining you the frequency that you got, and the amplitude. That is quite important because the amplitude is what is going to give you a reflector more or less brighter. Easy peasy. All things that you know, yeah?
What does X mean? Sorry.
X is the direction of propagation if the coordinate X. I have to define a certain point that is traveling along a direction. So you can call it X or you can call it Y, you can call it Z. But when I write an equation, I have to write the equation and telling you which direction is pointing the sinus, is moving the sinus, okay? In that case, it's X direction, and you got it both there and there. Fine. It's not a parameter, it's an independent parameter that defines you always traveling across. Boom, here we go. Now, what the theory says is that if I approximate my P wave that is reflecting on the surface, the physics is only that one. You got a reflected P wave and a transmitted P wave, and the summation of the energy of those two ones is equal to that one. Second question. Now, this is subtlety, but it's a subtlety that helps us to write the equation at a certain point. When I got, remember that associated to a P wave, you got some pressure. So we are applying an instantaneous pressure to the table. Okay? So there is a P wave is propagating, and we know by the earthquake that the P wave can move and move a lot. So you got a kind of movement and shaking of the system. Now, it moves a lot, but most of the time it moves, and when it's passed on, your house maybe has received some damage, but the soil come back more or less to the same position. Unless you have a breakage because you got the fault nearby. But the P wave and the S wave in itself is shaking the object, and then the object come back to the same equilibrium condition. A little bit broken, but equilibrium condition. This implies that the pressure that you are applying by that P wave and the component of the reflection that's and transmission are in such a way that at first the phenomenon now is for simplicity, for you to understand how it works. Geometrically, I put at a certain distance. But in reality, you should see those ones at an infinitesimal distance. So this is a kind of micromillimeter. So they are almost, the three objects, almost orthogonally nearby each other's. And the pressure done by that one through the transformation transmission to the reflection in such a way that the distance is instantaneously shaped, but as soon as the transmitted and the reflected go away, it comes back to the original position. So I don't create any breakage to the surface. This implies that from a kinematic point of view, not only energetic point of view, I need to conserve the distance. The soil was flat, without any breakage. After the pressure of the C wave and the transmission of the P wave, it comes back to the initial position. So preservation of the energy, preservation of the kinematic. Good. Now, this is the equation of the wave. You recognize it. My equation A0 cosinus Wt minus K1 Z. Now, I'm playing with a surface that is separating two objects that are defining the surface. They need to have a density and a velocity property. So it's like two piles of rocks. So it's a kind of two lithology and basically surface separated them. So one, I need to assign a value of the amplitude of the wave that will be an A0. I call it A0 because it's the original energy that it got. You can call it B, C, D. I call it now A0. The reflected one is the wave that is going on the other wave respect to the one that is reflecting. So I need to put a minus, okay, and I need to put an energy that now is an energy that has to be different respect to the first one. Why? Because is reflected but is a piece of the story, because there is another piece that is the transmitted there. The only thing that I know is that in terms of kinematics, the kinematic induced, so the shaking induced by that one, need to be equal to the shaking basically induced by the 2-1, or in terms of the sign, the total energy in there is to be equal to the total energy in there. How does it work? Well, remember that that one has positive sign is that one, so that one has a positive sign and that one has a negative sign. So, I describe the equation. The incident reflection plus the reflection there need to be equal to the transmitted part. So what I lose through the reflection, I gain to the transmission. I don't know which proportion, but I know that the total summation of that one is always correct, because the kinematic is telling me it's correct. Now, I write the equation of my incident ray, that is my A0 cosinus Wt minus K1 Z. Why I put in K1? Because in addition to the amplitude, even the wave number, I can put all the frequency, or the wave number as a characteristic of that signal. That signal is going through basically a medium that is different from that one. So I need to separate or the frequency or the wave number. Now, for mathematical reason, I strongly suggest you to follow that option. That is the option in which I'm changing the wave number. So I'm telling you that the wave have a property here characterized by a wave number defined by the medium, that is K1. So I expect the reflected wave back to have exactly the same K1 property. In fact, that's what I put. What is the difference is that the reflected ray needs to have a minus sign because it's going the way opposite. Good. Equal to what? To what we lost or preserve, it depends which is your opinion on that point of view, in terms of the transmitted wave. And the transmitted wave is nothing else that at different amplitude, because the energy related to those one is going to be different, but in that case, the wave number is going to be K2, because it's my second medium. Now, I wrote the question. Now, let's go it very, very simple. Because I cannot carry on this kind of baroque object in there. It's too long, it's annoying me. It's too much parameter. So now the physics is entering and is defining me the boundary condition. The physics tell me that in reality, all these kind of things that I represent in the diagram, they are in reality happening at a very millionth part of the millimeters. It's an instant piece in which the incident, the reflector transmitted, when you go to reflection, the two transmitted and reflected are instantaneously propagating, but everything is happening in an instant. So, the Z, basically, that define me my position, can be a Z that tell me that being the three wave at very short distance can be simulated as the limit towards zero. So limit towards zero imply that that one, and that one can be approximated as zero. The K1 multiplied zero. The K1 multiplied the limit to zero. The K1 multiplied limit to zero can be simplified as zero. But that's good, because that implies very simply that equation is nothing else than that equation. A1, A0, I mean A minus A1 is equal to A2. So the difference between the amplitude of the incident ray and the reflected ray need to be equal to the amplitude that is present on the transmitted wave. That makes sense, honestly, because I told you that you have to respect the energy conservation of it. So I expect that if you got the original incident ray that got all the energy, and then it's going to be transmitted and reflected, the summation of transmitted and reflection need to be equal. So proportionally, the difference between the two, or if you want, the initial A0 is nothing else than the summation of the reflecton plus, you took it the other way, to the incident. Clear? It's very clear. It's very simple. So it's telling you that a couple of things, the kinematics. Go to the principle. That when you see a reflection, so a reflector in your seismics, the amplitude in your reflector is just only part of the story. It is the one that is reflected. Because to see him, you need to go back to the geophone. And the one that's going back to the geophone is only part of the total initial energy of the shots that it was shooting during the experiment. Part of the transmitter ray disappear. Well, partly disappear because if you want to explore the subsurface, you need that a little bit of the transmitter ray is going to disappear below to do its job and reflect another times. Okay? So that's fix in your mind that relation because we are going to reuse it. Now we need to fix the boundary conditions that are the energy condition. And this is a little bit, probably a little bit if you want, but it's not complicated. So now energy, back to the physics, and back to the relationship between stress, strain, and elastic parameter. Now my problem is that I need to express. But let's do a step back. How do you define strain? You have a definition. You are geologists, all of you are geologists, some of them come from university, they got a very distinguished professor in structural geology. A lot of you, even in Aberdeen I got Butler, the other one got Daniel Kuhn, the other one got John Wheeler, wherever you are coming from, you got the notion of strain. How do you define the strain? Strain of a rock is it applies to seismology as well. Eh? So, how do you define the strain?
Change its dimension.
Pardon?
Change in dimension.
Dimension.
Is it the energy required to change?
Pardon?
Energy required to deform?
It's no energy. Strain is about, I would say rather than dimension, displacement. Because when you look at a rock that is deforming, so a fossil, a desperate fossil into a rock, then you deform it, it's not very happy, but you geologists you are, because you know the original dimension and you see the final dimensions, you calculate the strain between any kind of idealistic original dimension. How do you get to the final dimension? And the difference between the initial and the final give you a strain, a finite strain information. So strain is about displacement, how the points displaced during the deformation. Transfer that concept to the propagation of the P wave into a body. The body is propagating into a wave, into a body, it's shaking the body instantaneously. When it's shaking, it's instantaneously deforming. So the deformation produced by the P wave that is penetrating on it is proportional to a strain, that is the strain along the direction, and I call it the ZZ direction. So that strain is nothing else that sign, that Greek sign, is the derivative of the difference between the initial point before deformation and the final point after the deformation, right before the P wave is passing through. So it's a difference between position. What are these kind of numbers? Well, these are the elastic parameter. Remember that any P wave need to be described in terms of elastic parameter. So I'm telling you now, I'm introducing you, or reintroducing you, what I've introduced you before in terms of velocity. Remember, the velocity is the root between the elastic parameter divided by the density. Well, they come from that equation. They tell you that the stress produced by the P wave across the body is proportional to the elastic property of the rocks multiplied by the amount of strain that the P wave is producing doing the traveling across the rocks. The strain is a derivative. Now, what describes the vibration of the particle? Well, what describes the vibration of the particle is that equation, is the equation of my wave. The wave equation is what is describing basically my particle. Now, don't know if I got it. The first equation, that one, comes from a derivative of the original equation that, remember, was the amplitude multiply the cosinus of your frequency t minus, in that case, k1, multiply, in that case, is z, because I'm calculating along z. That was the original equation. Okay. If I do a derivative of that equation, it's a derivative of a function, and it's telling me that I have to do the derivative of the sine, of the cosinus, multiply, right. So, the derivative of my function, your function is a cosinus of something in between, inside. And what is inside of your function is your wave number multiply the velocity minus the wave number multiply x or z, or whatever you are. Doing the derivative respect to x, the derivative that is the derivative of my function is the derivative of the vibration of my particle. That is, I'm calculating the strain associated to the vibration of those particle produced by the passage of the P wave across the body. Now, the derivative of that is, by definition, the derivative of the whole function, that is my cosinus, the derivative of the cosinus is minus sinus. You just need to learn it. It's how it is. Okay? So every time you do the derivative of the cosinus or whatever, it's a minus sinus. Of what you got inside, I'm not going to write a kv minus kx again. Multiply what? The derivative of what is inside. And what is inside, now I have to write it properly. So, minus sinus kvt minus kx, we know where does it come from, is the derivative of the cosinus of that object, multiply the derivative of that object in there. Now, if I do the derivative of that object in there respect to x, any parameter that is not x is 0. So the only thing I have to derive is the one depending on x, that is minus k. So, minus a sinus of kvt minus x multiply the derivative of minus k, the minus and the minus multiply, I got a k a sinus kvt minus kx. Okay? So that's how you get to the derivative of the original equation. And I remind you, the original equation describes how the vibration of the particle are produced during the passage of the P wave across the body. If I do the derivative, I'm calculating the strain. This is the strain component of it. So that equation is nothing else that equation. Okay? Now, so I got my strain. Now what I have to do, I have to substitute my strain into this original equation. So all this kind of story, K1 A0 sinus of that one, okay, I'm calculating it for the wave that is basically incident to the medium 1, so K1, now go back to the original example we start for the kinematic, K1, whatever. You substitute that to the strain, and you got the elastic parameter multiply K1 A0 sinus, so all that kind of story. That's the stress component of it. Good. Now apply some of the relationship that I know. or I introduce you. Remember that relationship, the summation of the two elastic parameters equal to rho p squared, come from the definition of the p wave velocity. Remember, the v velocity of the p wave is the root of the elastic parameter. I introduced you that one in the previous slide, so it's not a really a new entry. It's just a way to reshape your new entry. Remember, the velocity was the root of lambda plus 2m divided by the density, all under root. Okay? If you square it, v squared is lambda plus the twice the component divided by rho. Rho in there, you put in there, so rho multiplied the v squared is nothing else than the two elastic parameters. So, why I want to substitute those ones? Because I don't like them. I want to use stuff that I know, that is the velocity. So, those one become my rho 1, v1, velocity square. Why v1? Because I'm the medium one. I'm using the k1, I'm using the v1. Okay? That equation is the relationship between frequency, velocity, and wave number. So write the wave number now, k1, in terms of the velocity 1, but it's the frequency divided by velocity 1. So that relationship gets a quality that comes from the definition of wave number, frequency, velocity. Is going to substitute my k1. And as it is a k1, it has to be v1, rho 1. That's my equation. Now I got my full equation rewritten in terms of velocity, frequency, wave number, and density. Don't have any more the elastic parameter because there were too much parameters. Well, what I have to do? I have to do the same gain I've done with the kinematic component. The energy of the object are an energetic object, incident, reflecting, transmitting, in a surrounded of a micro instantaneous, I would say, meter distance. So, I put my z towards 0, being the three variant short distance, and put everything is multiplied by z to 0. And what it remains is that one disappeared, and I write the equation in terms of the energy. So I write that the first equation is the equation of the first medium plus the component related to the reflected wave, that is at that component at value, that remember the value, equal to the transmitted part of that. So I'm using the relationship I use for the kinematic energy. But that object inside, you can see there are some common value on the both sides. So common value implies that one. The first common value are, I got the sinus on the both sides. You see it? Sinus there, in there, in there. So I can divide there with that one and that one. Gone. So what I got, and one other thing I got is that the frequency, that remember in my case the frequency, I didn't change it because I decided to change the wave number. Still there, there, and there. So done as well. So what will remain is my density 1 V1 A0 plus density 1 V1 A1, okay, the reflected one, equal to the density 2 V2 of the transmitted. Now it's much more simplified. Remember, how do I get there? I get there by imposing an equilibrium between the stress field or the energy related to the equation, and that equation comes from the definition of the stress-strain relationship through the elastic parameter. And the only kind of stupid game I did is to re-describe the strain function of the vibration of my particle, because the vibration of my particle are displacement, so the derivative is the strain. That has been the step-by-step. What you need now is that one, because that one is what you are going to use for the exercise. You know where they come from, which are the boundary conditions where they come from. Well, how can I solve that equation? Well, I still got a piece of the equation from before, do you remember? the A0 minus A1 equal to A2. Why? Why I use it? I know that the summation of this kind of difference between the incident minus the reflect is equal to the transmitted. I substitute that in my E2. So I rewrite my E2 in terms of A0, A1. And you got rho 2V2 A0 minus rho 2V2 A1. That's exactly the same. Now, you put in common the A1 with the A1, so you got the rho V1 plus the rho V2 multiplied by the A1, and the rho V2 minus rho 1 V1 multiplied by A0. That part and that part. That part go there is a minus. Ah! Surprise, surprise, what you got is the kind of classical relationship between the amplitude of the incident wave and the reflected wave is proportional to rho V2, rho 2V2, rho 1V1, rho 1V1 plus rho 2V2. This is rho 1V, the multiplication between density and velocity is called impedance. So it's telling me that the ratio between the two amplitudes, so the reflectivity is the ratio between the amplitudes, is nothing else but that relationship between the contours of impedance. That's something you have to understand and to use it. I show you how we get there. Now, let's look at this formula and try to think about the implication as in a practical way. What are the implications of those kind of equations? Right. Let me go through the other one. Let's go straight away to that one. On the left, I got the transmissivity, the transmission component. On the right, I got the reflection component. Okay? I'm expressing the ratio between the transmission A2 over the incident rate, so how much I lose in terms of transmission, and I'm putting on my right the ratio between the incident and the reflected one. Clear? So the one on the right is reflectivity, transmissivity. What those equations are telling me? First, now let's put the amplitude where it should be. I put the original amplitude is 0 on the other side so that I can really understand how the two amplitudes of the reflection and of the incident are related one each other. Let's start from the one on the right. Okay? A1 is all this kind of object multiply that A0. To give you an idea how you can calculate your density. You are a very good petrophysicist now. So how you calculate the density? Come on. Or you get density information from a well. You can get some information from the well. Yes. Actually, we show you, I'm sure that Jeff has shown you, or told me shown you, the Gardner relationship between the density and the velocity. So in case you don't have the density, but you got the solid velocity, you can get the density using the Gardner laws. So there are two parameters that if you are exploring, or you are using, well, basically data, you can get it. Yes. So it's nothing strange. Our parameter, you can start to touch it. It's telling me a couple of things. In order to be the amplitude of the reflection 0, so I don't have any reflection, it needs to be that object in there 0. That one will never be 0, because if those two are all 0, I mean, there's no physics. I mean, it doesn't exist, the body. But those two can be 0. What does it mean if those are 0? It does mean that they got the same contrast of impedance. That doesn't mean they've got the same density or the same velocity, but they have the same contrast of impedance. Same contrast of impedance, 0, then my reflection component is 0. If my reflection component is 0, imply that rho 2v2 and rho 1v1 are equal. If rho 2v2 and rho 1v1 are equal, that means the summation of that one is equivalent to twice rho 1v1. Do we agree with that? Because if rho 2v2 is equal to rho 1v1, I can express rho 2v2 as a rho 1v1. Then that's only rho 1v1 plus rho 1v1, so it's 2 times rho 1v1 rho 1, 2 times rho 1 V1. So that means that A2 is equal to E0. So the implication from the right to the left is that if that one is 0, I don't have any reflection, but all the energy is into the transmission. Makes perfect sense. So now you start to understand what they really mean. You start to interpret the reflection in how they should be. Now, other scenario. The difference between the two are very small, but bigger than 0. What does it imply? Well, it implies that I got a reflection. And the reflection is positive. So I got my reflector. So the contrast of impedance between the two objects, the rho 2v2 and rho 1v1, exists, and I see a reflector. The more it's brighter, the more this difference is pronounced. So the more you got a higher difference between the two objects. But what I can get in geology, I can get as well the difference of the value can be negative. What does it mean if it is negative? It means that I got the first unit, I got a contrast of impedance that is bigger than the one below. So despite there is more lithostatic weight on the second one because there is the first one on the top, for some reason the contrast of impedance is lower. If it is negative, my amplitude is negative. Negative amplitude exists and is a change of polarity. So I got my polarity of my seismics. If you found an object like that and change the polarity. So think and fix in your mind that as you are a petroleum geologist, that's something you are looking at, because if you got a sandstone surrounded by sandstone with oil, and you can have a sandstone below that is more compacted than the one on top, but the one on top is where the oil migrated. The one with oil migrated got as lower density and velocity, so more is really extremely high probability that got a lower contrast of impedance than the one basically this is on top. So what you can get basically is that the contrast of impedance has a negative or change of polarity. The change of polarity is usually one important requirement that you need to observe on seismics if you are around a bright spot associated to oil and gas penetration. Okay? Is that clear, all the story? Or you can play with parameter. What I want you to understand is where we come from, but how you play with those parameters.
Sorry, can you repeat that? So if you have, are you saying if you have a more dense rock on the top or a less dense rock? Missed that bit.
Oh no, that was the wrong one. Weird.